Assalamualaikum warahmatullahi wabarakatuh. Very good morning to everyone. So today we're gonna have our class through online session. So this class is about finite element method, basically for MEMS applications. So my name is Muhammad Farhanul Hakim. I'm a research fellow at IMAN UKM. So basically you can find me at level 3 in our buildings. If you want to have a further discussion, can call my number or email me directly, because right now we cannot have a face-to-face session. So I know that maybe most of you would like to use this FEM simulation for your studies. So maybe this class is not enough for you to cover and to go further for your projects. So anyhow, contact me directly, so I will try to solve your problem. Like maybe already one or two of you already start your simulation projects. So maybe another okay. So maybe others also would like to use this simulation to verify your projects. Okay. So the outline for this class is we're gonna start with I will describe why we need to do simulations instead of experimental works, for examples. Because it's kind of complementary for simulation and experimental to be together. And then some of the success story in Malaysia about simulations or theoretical works. And then in general about FEM simulation for MEMS. And then the reason why we use FEM for MEMS. And then next one is some of wrong idea or misconception about FEM that I have been observing since 2-3 years ago from the previous students, especially in IMAN. So I would like to emphasize what is the mistakes, and then I would like to share some of the tips to publish in high impact journals using FEM, and then the introduction for the software that we are using, which is COMSOLS. So this is a software mostly to solve multi-physics problems, and then the basics of this COMSOLS, and then the steps to do the simulations. So let's talk about success story of FEM simulation in Malaysia. So we have two guys here. One is I think 15 years old student from Permata Pintar, UKM, who did his internship in Germany with the guidance of Professor Ahmad Kamal from FKB. So even though he's still in the secondary school, but his work is kind of high level, equivalent to PhD levels in Germany. So another one is a PhD student at Coventry University from United Kingdoms. So he introduced a dimensionless numbers to measure heat transfer, which has been used by the manufacturer of luxury car or hypercar. So yeah, that's all. So why we need to do simulation? So actually we need to do simulation because we want to optimize and verify our proposed products or device in terms of design, geometry or materials, so we can obtain the highest performance before we go to the fabrication steps. So actually by doing these simulations, it can avoid the fabrication of the prototypes, where we need to test, and then we are actually doing virtual prototyping, where we could also obtain the expected performance. And then this can save a lot of costs and times for the industry or for the researchers, because we can concentrate more on the theoreticals without doing any prototyping or test or experimental testing. And then of course for us as a researcher, we would like to find a good agreement between theoretical and experimental works, and further on this can enhance our understanding to explain the mechanism behind our results. In addition, actually the simulation also will allow us to do something beyond our imaginations and be creative by simulating a complex structure which is impossible to fabricate. But if the complex structure could give a good performance, or it can be later on it can be fabricated with the advancements of the fabrication technology. So the simulation also will allow us to solve several physics or phenomena simultaneously,
in order to consider the real conditions where the device will be operating. So in this case, a lot of couplings, for example between thermals, acoustics, optic mechanics, electricals, need to be solved simultaneously in order to obtain to obtain the expected results. Okay, so here I would like to show you an example on how to use simulation in the industry level, where they will use simulation to simulate the prototype of their future products, for example. So in this case, it's a condenser microphone developed by Bulkage Denmark. So they use FEM simulation in order to optimize their products in order to obtain better performance, especially in this case they are looking to improve the mechanical side of the membranes in the microphones. Okay, so the second example here is a hearing aid device. So even with the simulation, they managed to have a very good agreement between the simulation and measurement of the device. And so this shows that the simulation can predict the performance of the device, and we can do a lot of optimizations before we go to the fabrication process. So in the case of MEMS, so as you know, MEMS is a combination of electrical and mechanical in a single systems, with the dimension around micrometer dimensions. So most of the MEMS device require to solve simultaneously these electrical and mechanical problems. So it is also necessary to perform a simulation to verify the theory before we go to the experimental levels. There is a few commercial software that has been used for MEMS simulations, such as IntelliSuite,
ANSYS, Conventorware. But however, this kind of software focusing on the two physics, which is mechanicals and electricals. But however, in a real situations or for real device, a lot of another physics, such as thermal or acoustical effects, need also to be considered together in order to get the optimized results. So nowadays, if you say about MEMS, even though the definition is micro electromechanical systems, but actually MEMS can encompass a very large domain, such as electrical, structural or mechanical, but also thermals, microphysics. In microphysics there is also acoustics, there is also fluid dynamics, MEMS also can be about optics. So these are very multi-physics problems. So if we consider exclusively electrical and mechanical, it could not enough. It's not sufficient to consider a complete MEMS systems. And of course, in the case of MEMS device, when we go to micrometer dimension, we have to consider a lot of scaling factor, which could affect our device, which behave differently compared to a macro scale device, for example. So in the case of MEMS, the sum of the forces can become significantly higher when we scale down the dimension to micrometer, such as initial resonance, electrostatic, or thermals, thin film damping. So for example, in the case of thin film damping, it will become higher when we will become higher in the MEMS device. So, but for piezoelectric device, the scaling is quite well compared to the bulky dimension device. So this kind of forces cannot be negligible compared to the bulk, when sometimes with a bulky device, this kind of forces is negligible.
So in the case of MEMS simulation, there is several challenge that we need to consider, such as the force that become significantly important when we scale down the dimension to micro or nanometer, as we discussed just now. For example, the thin film damping or the inertia forces. This is more related to surface effect. And then high aspect ratio multi-layered structure. So for certain cases where the structure is very complex with several layers, and the difference of the dimension is could be with the order of thousands. For example, one layer with a nanometer scale, and then another one maybe 100 micrometer scale. This thousand order of difference could make the simulation to be in the difficult situation. It's not easy to solve this kind of problem actually. So we better to to avoid this kind of structure by adapting our geometry to be more or less similar in the similar order. And then there is also a challenge related to materials. For example, there is a materials with non-linear characteristics, but also anisotropy and inhomogeneous properties. So the materials can behave differently at certain directions. This is true for piezoelectrics materials, for examples. And then there is also challenge related to the physics. For example, when we need to solve multi-physics problems, so how to consider several physics simultaneously when the equation is so much different. So somehow we need to make a simplifications, or for example do the integration at certain boundaries. And then for some cases where we want to consider the damping and the losses, which is time dependent problems, but also non-linear. So a lot of factors need to be taken into account. So actually a lot of MEMS device can be simulated and has been demonstrated in the literature. For example, in the case of RF MEMS, radio frequency MEMS, the device such as RF MEMS switch, tunable filter, antenna, and then there is also bio-MEMS, such as microfluidics, electrokinetic flow, dielectrophoresis, acoustophoresis, magnetophoresis. So in this case, the simulation could be very complex, where we need to play around also with the biological matters, and we need also to consider the solid fluid interactions. And then the third one is the resonant MEMS, such as gyroscope, surface acoustic wave resonator, or bulk acoustic wave resonator. This is basically can be done using piezoelectric device, and the difficulty of this type of MEMS, resonant MEMS, is when we need to consider the damping or the losses. There is also the last one is the sensors and actuators. For example, accelerometer, pressure sensor, micromirror, micromotor. So here I'll show you an example of simulations done using FEM. The first one is cantilever, which is normally used in atomic force microscopy, or where it can vibrate easily freely in one side, but fixed at another side. So from here it shows that the simulation can predict accurately the experimental results, where the results from simulation and experimental is quite similar. And the second one is piezoelectric bulk acoustic wave device using quartz materials. So from here we can predict the displacement at resonance frequency, and the simulation can calculate also at frequency domain, where we can swap the frequency of the device to predict the mechanical displacement. So why we choose FEM? So the thing is, there is a lot of methods to solve physics problems, such as FDTD or CFD, but however these methods are specific to a specific problem. For example, for FDTD, FDTD is a finite domain time domain, so it has been used mainly for wave propagation and optical wave. And for CFD, is mainly used for fluid dynamics or fluid flow problems. Then in the case of FEM, it can handle complicated geometries and boundaries, and then its versatility to interface a few physics to be solved simultaneously in one single systems, and possibility to solve also in 3D dimension, and then it can also solve a non-linearity effects due to damping or material properties, as we discussed previously, but also to solve a problem related to time dependent study, where we can measure the characteristic with which evolve in the function of time. However, from the past few years, I have been seeing a few misconceptions of FEM, or some mistakes that has been done by the students, where they assume that FEM can solve everything, but actually it's not true. So what we can simulate in using FEM is something which has a continuum dimensions. So basically it should be in the micro scale or macro scale. So our limitation in terms of dimension is starting from, let's say, 1 micron to a bigger size, but it still can solve a problem in the dimension of nanometer, but it is not really recommended. And then I saw also some of students use FEM to solve a problem related to single molecules or single atomics, like graphenes, but actually it is not created for such materials or for such a structure. So basically, when the structure is an atomic layer or atomic scales, this software it cannot be used. So we need to have some defined dimensions in our structure. And then for actually, if you want to solve something like in the atomic levels or molecular levels simulation, so I would like to recommend DFT based software like Material Studio, which use density functional theory, which is more suitable for such a structure. And also if we play around with chemical reaction, this FEM software is not really useful for that. However, there is some modules which can solve chemicals, but very limited in terms of beauty. So for example, here the physical domains that we can solve by using FEM is, here we have problems of mechanics, structural mechanics. For example, if you want to find the resonance frequency, the deformations, the stress by when you apply a load on the structure, a fluid flow, mainly in the case of microfluidics, electromagnetics, normally for RF lamps, but also optical wave. And then we have also some chemical engineering, and then acoustics, heat transfer, and then the multiphysics, where we can combine a few physics in a single systems to be solved simultaneously. Okay, so I know that for us as a postgraduate students, we need to publish in a high impact publications, but the thing is, can you rely only on simulation to publish in a high impact? Basically, it is not possible. It is not impossible. It can be done, even though usually people will combine the theoretical and experimental works together, so it should have a good agreement between the results from the theoretical and also experimentals. But however, I've seen a lot of paper actually can be published with only simulations, but however it requires a deep understanding of the theories and some novelty, maybe related to geometries or related to materials, but also it could be related to the modelings. So the thing is, it's possible to do publication on high impact journals with only FEM simulations. Yeah, this is the examples. The first one is from IMEN EKM, but it was maybe 5 years ago, and then others is mainly from my supervisor. If you check, basically it's a works related to FEM, and they publish in a, I suppose it's a quarter one journals. And if you saw this one, the PRL journals is a top journals in physics. So even by using simulation also, it's possible to publish in a high ranking journals. Right now, so I would like to share some of the tips and tricks in order to publish in high impacts using FEM simulation. So the first one is try to make complicated, not really complicated, but more complex model by the combination of a few physics together in a single model. So for example, in MEMS it's already you have already electricals and mechanicals that we need to solve together. But let's say if you add the effects from the environment, so then you need to consider the effects of thermals and optics in your systems. So with FEM you can solve, of course you can solve a few physics together. So this is the advantage that you can have by using FEM. Then try also to have to simulate a complex structure, which something new that in terms of the structure that has not been seen in the literature or in the journals. Even though it's some things that the structure is very complex, but if you can come up with a new results, it's considered as it's still okay to publish, even though you don't come out with experimental results. So I have seen some of this complex structure without any experimentals. So yeah, it still can publish in high ranking journals with these tricks. And then for the physics mechanisms, try to explain or to describe this the mechanism behind your results in terms of physics by doing some analogy with another mechanisms in, let's say, if you are solving optical problems, and then actually you can find the same mechanisms or the same trend in acoustic or in maybe in electricals. So this is, for example, I can say the resonance mechanism. For example, you can find it in electric, you can find it in mechanics, you can find it in optics. And then you need also to know that the basic equation underlying behind your simulation. So rewrite this basic equation, even though people already know this equation. So for example, in mechanics, a lot of equation will rely on Newton's law, or in optics they rely on Maxwell's law. So rewrite these things, so it shows that you know the basic equation. And then, yeah, this is important. This trick is you need to try your simulation models by validating with the experimental data. Even though you didn't do the experimental, but you can take from others. Let's say you read from some journals, and then you try to simulate that experimental data, and then if you can find the same results from that, that means your simulation is good enough so you can vary the another parameters. Maybe for example, let's say if you read experimental works about so another tips is actually by the FEM software, you have also possibility to do a post-processing of the results. So for example, you can show the result differently by doing integration or derivations, or for example by doing some mathematical operations later on, and also the graphical operations. So this can shows that the result is this can show the result differently, and then it's more clear to the reviewer, for example. And then if you are totally new in a FEM simulation, I would suggest you to refer to the library models, so you can know that what is your capability in the simulation. For example, if you are looking for a current voltage curve, so if you saw models which can come up with that curve, so basically you should also capable to do such things, and also you can follow the steps from the library model. And then once you come out with the results, verify the convergence to check your consistency of the results. This can be done by I will explain later on for the convergence. So and then in the geometry, we should try to avoid a difference in the geometry in let's say in the order of thousands. So for example, the minimum size for your structure, let's say, is 1 micron, and then you cannot have another structure with 1 millimeter or 1 centimeter. The difference is too big, so the software could have some problems to adapt to this difference. So right now, I would like to introduce to you the software that we will use. It's called COMSOL. So COMSOL already been developed 20 years ago by a Sweden company, and then of course it can do integration of modeling from different environments to couple some physical effects such as electrical, mechanical, acoustic, heat transfer, fluid in one single system. Of course, it can also can be also being used together with another software like Excel or MATLAB for to develop a custom application. So the thing is, right now we would like to discuss what is FEM actually. So finite element method is actually based on partial differential equation, or PDE. So the first thing we need to do is to limit the system by creating the boundaries of what we like to solve, the boundary of our systems. It gives an approximate solution of the problems, and it's a numerical approach to get the real results of from the partial differential equation. So what we need to do is from a continuous physical problems, where we define our problems, and then we transform it into a discretized finite element problems with unknown nodal values. So this is what we need to do. Is the first step that we need to do is to divide the problems or our domains into non-overlapping regions, or called elements, which is connected to each other through special point called nodes. So here we have the elements, and then we have also nodes. Nodes is more like a point. So we need to define our boundaries of our systems So in this case, for example, you can see something like a T structure where we create a point in that in our models. So after that we can come up with the calculation of each point. So basically the three basic steps of FEM is called pre-processing, solver, the second step is solver, and the third step is post-processing. So the first step is pre-processing. It consists of creating the geometry and putting the materials into each domains, and then we need to define the physics, what we need to solve, the load that we want to put, the boundaries, let's say the physical properties that we want to put into that boundary or into that volume domain, and of course the equation, the basic equation behind to solve the problems. So let's say if you want to solve piezoelectric problems, so we need to choose the right models and the right modules, which are using only Hooke's law or Newton's law equations. And then we need, after that we will mesh the models or our geometries, where we will create this the small elements by putting a lot of points in between, and then we go to the solution and then the post-processing. So in the pre-processing steps, here what we need to define is the geometry, whether it's 1D, 2D or 3D. So and then once we already finish with the drawings, we will assign the material properties to the domains. Let's say one domain we will have one materials, and then another domain which is connected. So it cannot be a space in between domains. So maybe another material B in the domain, in the second domain, and then we need also to define the physical environment, mathematical equation to the models, and then apply the appropriate loadings, boundary and initial conditions, and also the assumption to simplify the simulations. And after that we will discretize the model into finite elements, also called meshing. So once you already decide the simulation that you want to perform, so basically you should know that the equations, the governing equations behind every problems. So for example, in the case of solid mechanics, they rely on Newton's law, mainly on and then for fluid mechanics they will rely on Poisson equation, and of course once we already know the equations, we need to transform it into partial differential equations, something like in these forms, and then after that we will convert it into in the matrix forms in order to solve the equations. Okay, so the next steps in your simulation is to give a assumption to your model. So this assumption can simplify the calculation, so you get your results in the shorter times, and the simulation will calculate it faster. So let's say, for example, you have a three-dimensional problem, so you can reduce it to two-dimensional. In the case of let's say you don't have a very big significance in the third dimension, or the third dimension is in a, let's say, 1000 order, 100 times bigger than the surface. And then, for example, you can also do a symmetrical. This is for the case, for example, a circular. It's a kind of a cake. So you can imagine you slice the cake, and then you just calculate a small portion instead of calculating the whole cake. So another way is to impose a periodicity. This is for example, if you have something like a crystal structure where you have a periodic repetition in either one or two direction or three directions, so we can just impose a periodic condition at the boundary and consider it as a unit cell. So the last steps before we solve the problem is meshing. So meshing is a kind of defined as a set of points and cells where it's connected to form a network. So this point is a local solution for the equation, and then we need also to consider that let's say if you have a joint, so we need to refine the meshing at that area. So, and then what you can do is you can increase the number of elements or nodes, which is supposed to improve the accuracy of the solution. But let's say this will increase the computing times. So actually the right numbers should be you should find the right numbers or optimum numbers of machines or elements, and then yep. Okay. So after that we just need to solve the problems. So once we already know the equations, so that one you can check from the software what's the governing equation behind. So let's say we solve a set of linear or non-linear algebraic equations simultaneously to obtain other results, and then such as displacement values at different nodes or temperature values at different nodes in the heat transfer problem. So after that we just need to click solve or compute, so and then let the computer do the jobs. And then the last part, once you finish the calculation, and then we need to do a post-processing. So in this steps we just analyze the obtained results by performing additional mathematical operations like integration, derivation from the raw data in order to get another value, or in order to get let's say for example in the case of mechanical structure, you want to deduce your modulus. so we can get it from the displacement and the stress, but so we need to perform some calculation before we can get the value. So another thing is we can visualize the result differently by performing slice or maybe visualization on the surface, and then we can do also the plotting of the results to get a graph either in 1D or 2D or 3D dimension. And then it's recommended also to verify the results by doing convergence calculations. So this is the whole steps of the simulation. So let's say from the start, the pre-processing will take around 70% of your time and your effort, where we need to define all the parameters, all the geometries, the materials, boundary condition loading, etc. And then but also the meshing, and then the solver steps. So these things is normally is 5% of your effort, because we let the computer to calculate. And then another 25 is from the post-processing, where we try to validate our results and then do the optimization and do the repeating. So for verification, actually what you can do is you can try to verify your model with the other source, let's say from the publication in the literature. So try to simulate the models from the literature and try to get the same result or in the same order. Yeah, and then we need to do also the convergence steps. This is can be done by using a pioneer meshing, where we create a higher number of elements or nodes, but it will give a result which is consistent. So we run from bigger mesh to smaller mesh, but we get a consistent result. So this will verify your convergence. Another way is to do hand calculation if possible. So as conclusions, the advantage of COMSOL is in terms of the materials, we can consider homogeneous, non-homogeneous materials, isotropic, anisotropics, even temperature-dependent material properties. We can solve non-linearity problems. We can import from another software, let's say from CAD software, the drawings, for example AutoCAD, CATIA or SolidWorks, which is more convenient to draw complex geometry. So we can just import the structure to the console to do the calculation. It has a user-friendly interface, and then it has also a possibility to be integrated with another software like MATLAB, Excel, and etc.